A 131 kilogram wooden crate rests on a wooden floor. The coefficient of static friction is 0.55. Part A asks for the greatest horizontal force we can apply without moving the crate. Part B says to keep applying that same force after the crate begins to slip. With a kinetic friction coefficient of 0.33, we must find the resulting acceleration. The conceptual hinge is that static friction adjusts to the situation, whereas kinetic friction has a definite magnitude. We will organize the solution with the full Newton's second law strategy. First, draw a free body diagram. Second, define coordinate axes. Third, decompose forces into components. Fourth, write Newton's second law equations. These 4 steps remain the strategy even when a particular step is easy. Here, every force already lies along a coordinate axis, so the component step will be brief, but we will state that explicitly instead of silently abandoning the method. The system is the crate. Replace it with a dot and identify every external force. The applied force points right. Because the crate remains at rest, static friction points left and matches the applied force for now. Gravity pulls downward with force mg, and the floor pushes upward with the normal force N. Omitting this vertical pair would make the diagram incomplete and would leave us unable to calculate friction, because the friction relation contains the normal force. Choose positive x to the right and positive y upward. Every force is already parallel to one of those axes, so step 3 requires no trigonometry and creates no additional components. For step 4, apply Newton's second law separately to each direction. The crate is still at rest, so both acceleration components are 0. Horizontally, applied force minus static friction equals 0. Vertically, N minus mg equals 0. Therefore, the vertical equation gives N equals mg. Before doing arithmetic, count unknowns. Applied force, static friction, and the normal force are 3 unknown quantities, but Newton's second law supplied only 2 independent equations. We still need the physical relation for static friction. Static friction is not automatically mu sub s times n. It adjusts to prevent relative motion. If we push with 100 newtons, static friction supplies 100 newtons in the opposite direction, provided that value does not exceed its limit. The correct general statement is that static friction is less than or equal to mu sub s times n. This problem asks for the maximum applied force without motion, so it places us exactly at impending slip. Only for that limiting condition may we set static friction equal to mu sub s times n. The vertical equation gives N equals mg, 131 times 9.8, or 1,283.8 newtons. At the threshold, the applied force equals the maximum static friction force, mu sub s, times n. Multiplying by 0.55 gives 706 newtons. This is the greatest horizontal force that static friction can balance. The crate is on the verge of slipping, but its acceleration is still 0 at this limiting instant. Once the crate slips, keep the same applied force of 706 newtons. The system, coordinate axes, and vertical forces are unchanged. The horizontal friction force is now kinetic friction, equal to mu sub k times n. Because 0.33 is less than 0.55, friction suddenly becomes smaller, while the applied force stays the same. The complete Newton's second law strategy still applies. The force diagram changes only where the physics changes, and the new horizontal imbalance produces acceleration. The vertical equation still gives N equals mg, so kinetic friction is mu sub k times mg. Horizontally, applied force minus kinetic friction equals ma. From part A, the applied force is mu sub s mg. Substitution gives mu sub s mg minus mu sub k mg equals ma. The mass cancels, leaving acceleration equal to the difference of the two friction coefficients times g. Numerically, the acceleration is 2.16 meters per second squared in the direction of the applied force. The maximum force without motion is 706 newtons. After slipping begins, the same applied force produces an acceleration of 2.16 meters per second squared. Because kinetic friction is smaller than the maximum static friction, the reusable method is the full four-step Newton's second law strategy. Draw a free body diagram, define coordinate axes, decompose forces into components, and write Newton's second law equations. The crucial friction check is separate. Static friction adjusts up to a limit, so use equality only when the problem actually places the system at that limit.